and welcome everyone to the fourth session in APA's training series on engineered wood products. I'll be presenting APA recommendations on I-joists in residential roof systems. Individual manufacturer recommendations may differ. You should consult appropriate manufacturer's literature when specifying any engineered wood products. Now, I-joists are often used in commercial roof applications, but today's training module will focus on residential pitched roof systems. So our training objectives for today are to help you be able to identify and describe the best practices in designing and detailing residential engineered roof systems, the proper techniques for connecting, notching, and drilling the I-joists in those systems, and of course the correct use of web stiffeners and blocking in the same systems. Now today we'll be reviewing installation recommendations based on APA I-joist construction details. Performance-rated I-joist roof framing details, Form D710, is the base of our training today. Now this diagram calls out the various framing details that we'll be looking at. You can also find this information on page 8 of the publication. So first, let's start with a very common assembly where rafters run into a ridge beam. As we know from previous modules, the attachment of dimensional lumber to walls and beams is a bit different from that of I-joists. This detail is used for monopitch or shed-type roofs where the rafters bear on a wall. Don't notch the bottom flange at the wall, but on this detail, instead use an extra wall plate that has been tapered or beveled to match the roof slope. Attach the beveled plate to the wall with 16-penny nails at 16 inches on center. If the pitch is greater than 412, connectors are required to resist lateral thrust. Those connectors need to be engineered to transfer the thrust. The bottom rafter flange is attached to the beveled plate on each side of the web with a minimum of one 10-penny box nail. This is the same recommendation as when attaching I-joist floor joists at the bearing. Rim board or I-joist blocking panels are placed between the ends of the rafters to provide lateral stability. Continuous 23/30 seconds performance category sheathing panels can also be used across the ends of the rafters for lateral support and for closure. The blocking panels or continuous sheathing panels should be attached to the top plate of the wall with 8-penny nails at 6 inches on center with a minimum of 3 nails per blocking panel. If the roof system is a designed diaphragm, the nailing of the blocking panels must match the nail type and spacing used in the boundary nailing of the diaphragm, but a minimum of an 8-penny nail must be used. Now, in case the end reaction of the I-joist exceeds 1,550 pounds, the bearing stiffeners need to be used to support the I-joist webs. Manufacturers of proprietary I-joist products might have different web stiffener specifications and, of course, loading amounts. So consult with the manufacturer's literature with regards to those stiffeners. All nails shown in the details that we will discuss during this presentation are common nails unless otherwise noted. 10-penny box nails may be substituted for 8-penny common nails in all these details. Here's another monopitch roof detail, this time using a ridge beam instead of a bearing on a wall. In this assembly, adjustable slope metal hangers are used to connect the rafters to the beam and to support the vertical load as well as laterally supporting the rafters. The hangers must also provide a minimum of 300 pounds of uplift resistance. The rafters are cut to fit the angle between the roof pitch and the plumb beam with the required wood stiffeners also bevel cut to match that angle. A strap tie is used to connect the rafters tight against the ridge beam. The straps are fastened at a minimum of 3-inch spacing or in accordance with the strap manufacturer's recommendations. Note that all of these details may require additional connection for the assemblies to resist uplift forces. Now here we see another ridge beam assembly, this time with rafters coming into both sides of the beam to form a gable-type roof. The details are all the same, with the exception that the strap now connects opposing rafters to each other. In this picture, we see obviously a cold weather installation of the detail from the last slide. Note that the rafters along one side of the beam are already in place with straps ready to be bent into position and secured. When doing overhead work, it's often more convenient and safer to put the connectors in place on the ground. In this case, the sloped connector and wood stiffeners could be placed on the ends of the I-joist before lifting them into place. It's also possible that the flat strap could be pre-nailed to the joists on the right-hand side of this photo as well. Now we're going to take a look at how to support our I-joist rafters on the top of a beveled ridge beam. As was the case in detail 1A, blocking panels are used to laterally support the rafters. Blocking panel to beveled plate, rafter to beveled plate, and beveled plate to beam connections are the same as specified in detail 1A. Instead of metal straps across the top of the rafters, the webs of the rafters on each side of the beam are connected with gussets. The gussets are made from a 24-inch piece of 23/32 performance category sheathing that's been cut and attached to both sides of the opposing rafters. Those gussets are fastened to each rafter with 12 clinched 8-penny common nails. As with all panels fastened to the web, there should be an 1/8-inch gap between the top of the panels and the bottom of the top flange. Now this is detail 1E. It's a similar detail, but instead of using gussets to tie both sides of the roof together, we're using metal straps similar to what was done when connecting sloped rafters to a flush ridge beam. The straps should be nailed a minimum of 3 inches apart, but begin fastening at least 2 3/8 inch away from the peak of each rafter. All else is the same as we saw on the last slide. So we're moving down from the peak of the roof, and then we're framing in a skylight or other type of opening. This is the same thing that we did when framing an opening in the floor system. We have double rafters or trimmers on each side of our opening with filler blocks between the webs of the doubled rafters. Backer blocks are only required behind the hangers on the hanger side of the rafters. When top flange hangers are attached to I-joist headers, a backer block must be installed to prevent the top flange from rotating under the load. Backer blocks should be installed snug to the top flange with a minimum of 10 10-penny nails clinched. Here's another roof opening framing assembly, but this time using face mount hangers. When nailing into the web area, we need backer blocks on both sides of the rafter's web, and that attachment uses 12 10-penny nails that are clinched on the back side of the assembly if possible. Obviously, with any of these assemblies, loads must be calculated to make sure that the header beams are sized correctly. We may find ourselves using LVL, glulam, or another type of compatible depth engineered wood beam material. Otherwise, everything else is the same as in detail 1F. So now we've slid down the roof to the eave and looking at the location of the rafter bearing on the top plate of the exterior wall. This photo shows a cathedral ceiling roof application where the bottom flanges of the I-joist rafters will be used to support the ceiling of the room. In these applications, insulation will be installed between the rafters with space above the insulation to allow for fresh air to move from the soffit, from that area outside the top wall plate to the ridge. As energy codes become more strict, more and more insulation will be required in ceilings, whether they be cathedral or attic type roofs. In this detail 1H, a bird's mouth is cut into the bottom flange in this detail, and the load is transferring through the rafter and supported by bearing stiffeners on both sides of that rafter. The stiffeners have been bevel cut so they're plumb above the bearing surface, tight against the bottom flange, and have 1/8 inch space between the top edge of the stiffeners and the bottom edge of the top flange. The stiffeners are attached to the web of the I-joist with 2 8-penny common nails from each side and then clinched. Manufacturers of proprietary I-joist products might have different web stiffener specifications, so please consult their literature. And as always, 2 10-penny box nails attach the bottom flange to the top wall plate, one on each side of the web. In these cases, more nails don't make it better. In this detail, we're just adding blocking panels to detail 1H. As always, the blocking panels are attached with 8-penny common nails, face nailed at 6 inches on center, with no fewer than 3 nails connecting each blocking panel to the top plate. Details 1K and 1S go a step further than detail 1J and create a way for the I-joist rafters to support up to a 24-inch soffit area at the eave of the roof. The bottom of the rafters are beveled to be perpendicular to the wall at bearing height. Dimension lumber blocking is then added to one side of the bevel cut web to support the fastening of the soffit system and the fascia boards. The 2x pieces are attached through the web with 8-penny common nails, 6 inches on center, and then clinched. When using the bird's mouth cut details, the outside corner of the blocking panels may need to be trimmed so they do not extend over the top edge of the rafters. This trimming is allowed in this case. In details 1M and 1Q, a beveled plate is used instead of cutting a bird's mouth in the bottom flange of the I-joist rafters. Web stiffeners are not necessary in this detail. It's important to note that when beveled plates are used, additional fastening of the rafter to the supporting wall is required because the downward pressure at the beveled plate causes a thrust inward at the top of the supporting wall. These forces are not present when a bird's mouth cut is used. This often requires framing anchors due to the limited space for fasteners over the beveled plate. When bevel cutting I-joists, APA recommends that the cut does not extend beyond the inside face of the bearing wall or beam. The full depth of the I-joist is to rest in part on the bearing wall or beam. Some manufacturers publish design recommendations and details for beveling I-joists beyond the inside face of the support. So consult the specific manufacturer's literature before detailing I-joists or notching I-joists beyond that inside face of support. Now, along the rake or sloped edge of the roof, there are commonly overhangs that extend beyond the outside surface of the exterior end wall. To accommodate these overhangs, detail 1P was developed using dimensional lumber framing that extends flush to the top surface of the first rafter that is set inside the exterior wall. The end wall is framed higher for this purpose as shown in the diagram. This is similar to regular stick frame construction in this area. Note that the flanges of the I-joist rafters are not to be notched or cut in any way. Maximum overhang for this type of design is 24 inches. Detail 1R is another way to support a soffit from I-joist rafters. The ends of the rafters are trimmed flush and plumb with the exterior wall framing. A 2x4 lumber piece is extended up the slope of the roof for a minimum of 48 inches and extends beyond the end of the rafter to 24 inches. 2x4 is then attached to the web with the top of the 2x4 1.5 inches below the top surface of the top flange with one row of 8-penny common nails at 8 inches on center and then clinched on the other side of the web. Overbearing, a 2x4 is bevel cut at the top and the bottom to fit flush against the top and bottom flange and the bottom of the 2x4 overhang support. Then another piece of dimensional lumber is nailed to the top of the overhang support to provide a flush extension for the roof sheathing and attachment to the top of the overhang. Here's another overhang detail using a beveled plate. In this detail, the end of the rafter is cut to create a horizontal attachment for the soffit and vertical to create a flush attachment for the fascia. This removes a portion of the bottom flange and some web material as shown by the diagram. A 2x member is then attached to one side of the horizontal cut in the web and then beveled on the end to be flush with the angle along the top of the bottom flange of the rafter. The short 2x piece is then attached to the web with 8-penny common nails at 6 inches on center and clinched on the back side of the web. The underside of the roof sheathing should be ventilated. Detail 1V shows details of bird's mouth cuts in the top of the blocking panels located above the top wall plate and between the rafters. As shown in the drawing on the right, angle cuts can be made in the center third of the top half of the blocking panel to provide ventilation between the ceiling insulation and the roof sheathing. If this area is not protected by a vented soffit, then a perforated mesh of some kind should be placed over the cutout area to keep insects and birds from nesting in the area under the roof. Keep in mind that energy codes are encouraging the use of deep insulation over the top plate of the exterior walls, so the cut should not extend below the thickness of the insulation in those areas. After looking at ventilation solutions at the lower bearing, let's look at a detail for the peak of the roof where a flush ridge beam is utilized. In this illustration, the I-joists are raised above the ridge beam enough to create the required free area for ventilation through a ridge vent system. It's important to note as well that in other assemblies we have examined today, the blocking may need to be notched or drilled to ensure proper ventilation. Check with your manufacturer for a specific recommendation in those cases. It's critical that the required depth of insulation be taken into account when specifying joists used in a roof assembly. There must be enough remaining depth for the correct airflow to occur when ventilation is required. Energy conservation and moisture management must be considered in roof and ceiling design. Increasing the amounts of insulation and the levels of airtightness are required. It leads to the development of new concepts and systems. While increasing energy efficiency is the ultimate objective, managing moisture as it migrates through the roof and ceiling systems must always be addressed, making ventilation design critical to the long-term performance and the durability of the components. Roof ventilation systems not only keep attics cooler in the warmer months, but they also facilitate air movement over cooler surfaces, such as the bottom of the roof sheathing and roof rafters, which minimizes moisture condensation. This air movement promotes drying and carries moisture outside through the upper level ventilation devices. It's important that I-joist roof systems address not only the structural requirements of the building code, but also the energy and building science requirements as well. Now this concludes our presentation on roof framing with I-joists. Before we sign off, I'll review the training objectives and then review some APA resources that you may find helpful. So hopefully today, after completing this training, you're able to better identify and describe the best practices in designing and detailing residential engineered wood systems in the roof, the proper techniques for connecting, notching, and drilling those I-joists in the systems, and of course the use of web stiffeners and blocking in I-joist roof systems. Now just a note on fire protection. Both the 2012 and 2015 versions of the International Residential Code include fire protective membrane requirements to enhance the fire performance of residential floor systems. APA has a wealth of information about designing I-joist floor systems to meet the IRC requirements, including a recorded webinar you can watch online, as well as downloadable publications and CAD details. If you have any questions about I-joists and fire protection, please visit our website, apawood.org/I-joist-fire assemblies. And these resources are all available for free. APA has resources available for you as well. We all need help from time to time, and the APA's Product Support Help Desk is a great resource for answers to those questions that you run into during your work with engineered wood products. Help Desk is a free service. It's available to answer your questions pertaining to the specification and application of engineered wood products and systems. Staffed by specialists who have the knowledge to address a diverse range of inquiries related to engineered wood. So it's a great resource, great for your customers, builders, designers, and code officials as well. Now, our APA Field Services team consists of full-time engineered wood specialists located throughout North America. These professionals include engineers, architects, construction experts. They're all available to provide information and recommendations to construction and design professionals. We recommend you get to know your APA engineered wood specialist in your area. Now, we've updated and redesigned our apawood.org site. The site holds a wealth of information about products and their recommended installation requirements, and all electronic downloads are free. Take a few minutes to explore the site so you're familiar with the resources that are available for you. As well, on our wood site, the APA website is a list of all the APA members, including their complete list of the manufacturing facilities and the sales contacts for each. APA has a large selection of literature, some which will be referenced during our training modules. All of these documents are available for free download from our website. And finally, from the apacad.org website, designers can download many different details that can be dropped directly into their designs. It's a great tool. So this concludes our training module. I appreciate your attention and time today, and I'll turn it back to Marilyn.
So let's turn to the first question, Darren. Can I-joists be cross-ventilated in a roof application?
The answer to that is yes. And of course, it depends on the depth of the insulation versus the joist depth, but it can be cross-ventilated. Check with your specific manufacturer for guidance as to hole cutting or utilizing the knockouts in the joist for cross-ventilation.
All right, thank you. Here's the next question. You didn't cover much on uplift. How do I design for wind uplift?
That's a good question. Of course, uplift designs vary based on your location, the area wind speed, building exposure, and other factors. So it's always good to consult with your product manufacturer or your local code agencies to find out the details related to your location and situation. So there's not one size or one detail fits all for that. So a little more specific, so check locally for an answer to that.
All right, thanks, Darren. And then here's another question. Do the joists always need to be doubled next to the framed openings in the roof?
That's a good catch. It's not always. Of course, it depends. The doubling requirement depends on the size of the opening and the loads involved. So most of the time with proprietary software, you can calculate whether a single or a double joist will be required, or in some cases moving up to a beam, LVL or glulam type beam. So it's always good to use the software and know for sure.
Okay, and then one more question for you. Is there a maximum pitch for I-joist use in roof systems?
With that question, we'd have to refer you to the manufacturers. They all have max pitch or special design requirements stated or noted on their literature. So check again with your specific brand or manufacturer for details regarding that question.
Okay, thank you, Darren. And thanks again to everyone who joined us for this morning's webinar presentation. Don't forget to visit apawood.org for more information on this and other webinars in this series. This ends today's webinar. Thank you.